Hello there. Today I'm going to be talking about deploying state-of-the-art deep learning models in under an hour. But first, an introduction. Hello, I'm Fred Rice. I'm the Chief Architect at IBM's Center for Open Source Data and AI Technologies. We are an open source lab located in San Francisco, California. We focus on foundational open source technologies for data and AI, including technologies centered around today's topic, deep learning. But enough about me. Let's talk about you. If you are attending this talk and you've read the abstract, you hopefully are somebody who wants to deploy the latest AI technologies in your enterprise applications. Maybe you're an application developer, someone who has been given a deep learning model to deploy in an application. Maybe you're an enterprise architect who is looking to decide how best to use these state-of-the-art deep learning models across an architecture. Or maybe you're a data scientist who is responsible for deploying your own models in the context of an enterprise application. In either case, we're going to give you the knowledge in this talk about what are the best practices, what are the best tools for using deep learning in an enterprise application. But because of the broad audience, I'm not going to assume that you know about deep learning starting out. We'll have some material at the beginning that explains that. In particular, we'll start out with an introduction to what is deep learning, and then we'll move into best practices for deploying deep learning in an enterprise application and move on to tools and techniques by way of an on-screen demo. Let's move into the technology section of the talk. What is deep learning? Now, before we get into describing what is deep learning, we're all going to need to be speaking a common language. Now, machine learning, like many areas of computer science, has over the years taken some words from the English language and given them special meanings. Just like in the application space, if you say to a non-developer, I'm going to use a socket to send JSON to the server, because of the words you're using in that sentence having other meanings, that could create a somewhat strange image in the head of someone who is hearing that for the first time. So we need to take some words from machine learning and make sure that we all understand their meanings so that we can understand the rest of this talk. And the particular words I'm going to be focusing on are model, weights, features, training, inference, and predictions. So very briefly, a model in machine learning is a computer program. It is a computer program wrapped around a mathematical formula with some glue code to make that formula run. The formula itself consists of some constants and some variables, and values for those constants are called weights. Values for the variables, which change every time you evaluate the formula, are called features. The process of choosing some good weights, some good values for those constants in the formula is called training. And the process of executing the model, that computer program in the context of an application is called inference. And the result of that execution is called predictions. Now, I'm something of a visual learner, so I can best conceptualize these concepts when we put it in a picture. So I'm going to use a picture to describe the relationships between these terms for the rest of the talk. And we'll build this up step by step. So again, at the center of any deep learning or machine learning model is a mathematical formula, which you can see at the center of the screen now. The process of training takes some features, some values from a data set of the variables in that formula, and chooses values for the weights, some good values for the constants in that formula, so that if you evaluated the formula, you would get good results in the context of this application. We then take those weights and the formula and wrap them up with some glue code to produce a model, which will then take features from the application, values of those variables from the application, and evaluate the formula to produce results that we call predictions. And this process of producing these results, we call that inference. Whew. So that's machine learning in a nutshell. And that's the end-to-end process. Sometimes this is easy, sometimes it is hard. So as I said at the beginning of this presentation, any model in machine learning, and deep learning is a type of machine learning, any model in machine learning is going to be a computer program wrapped around a formula with some weights that give values to the constants in the formula, and some glue code for getting data into the formula and getting results out of the formula. And a deep learning model has that exact same shape, except that the pieces are a little bit oddly sized compared to a more conventional type of machine learning model. So at the core of a deep learning model is the neural network graph, which represents the formula. And then there's a set of weights that parameterize the formula. Now, because each node in this graph is actually a composite node representing many pages of calculations, the weights are actually much larger in practice than the graph itself. You may have hundreds of weights for each node in the graph. So it's important to note that although it looks like in this picture the weights are about the same size as the graph, no, they're 100 to 1,000 times larger in terms of their memory consumption, in terms of what you have to do to manage that part of the application. And the third part of the deployed deep learning model is the glue code, which is physically much smaller than the graph and physically much, much smaller than the weights, but it is equally important both to performance and to accuracy, because every bit of data that goes into the model and comes out of the model is going through that glue code. If the glue code introduces a subtle error, your results are going to have subtle errors. If the glue code runs slowly because, say, the execution of the graph is accelerated by hardware but the glue code is not, your performance will suffer. So glue code, even though it's small, still a very important part of this three-part harmony that makes up the deep learning model. So now we have covered deep learning models. Let's talk about how we use this technology in an enterprise application. And I'm going to center that portion of the discussion around some best practices. In fact, 5 best practices. Use the right tool for the job, identify the 3 components of the model, manage each of those components appropriately, build data acquisition into your architecture, and plan for explainability. Let's start with that first one, using the right tool for the job. And this best practice centers around not what framework should you use for deep learning, but should you use deep learning for a particular AI task. Now, if you take all of the problems that you might solve with AI in the enterprise, and you imagine ranking all of these problems along a spectrum from the ones that are easiest to most difficult for a computer to solve, easiest for a machine to solve, most difficult for a machine to solve, well, you'll get something like this. At the easy end of the spectrum, you'll have things like add up 1 million numbers to find this year's revenue numbers. That's super easy for a computer, maybe a little hard for a person, but super easy for a computer to conceptualize and run that program correctly. At the other end of the spectrum, we have the tasks that are impossible for a machine to do with today's technologies. And in the middle, well, that's where we have the tasks that you've probably heard about in the news as new AI breakthroughs recently, things like finding objects in images or translating text from one language to another. Well, these tasks in the middle that are difficult but not impossible for a machine learning people have a name for these kinds of tasks. They call them interesting tasks because they're hard enough to be an intellectual challenge, but not so hard as to be frustrating. And because these tasks are interesting, most AI competitions, be they Kaggle competitions or competitions among academics to meet benchmarks, tend to be centered on these interesting problems. It just so happens that the deep learning technology we've been talking about is by far the best technology for nearly all of the interesting problems that people are solving today. However, the problems that you'll see in the context of any enterprise application aren't necessarily all going to be interesting ones. They're going to span that entire spectrum. Some of them are going to be super easy for a machine to solve. Others are going to be beyond the capability of today's machines with today's algorithms. So it's important to seek the advice of someone who has the necessary knowledge to take a particular problem you want to solve with AI and put it at the right place on that spectrum. Someone who understands your business and has a good understanding of what kinds of problems are hard for a machine to solve. And then, if you don't have someone of that type, of that capability on your staff, it's a very good idea to have someone like that on retainer. And once you've synced the advice on the particular task you're focusing on. What you want to do is choose the simplest kind of AI technique that's going to work to get that particular job done. If you have a problem that is easy for a machine to solve, you'll have a happier time if you use a simpler technique that's going to give you just as good results, but with a lot less complexity. You might have an analyst run some reports on your data warehouse to determine some static policies that really work well according to the statistics. You might use a more traditional machine learning approach involving feature engineering. It's only if the problem really is a difficult but not impossible one that you want to roll out the big guns and deploy a deep learning-based solution. So it's very important to be able to make that determination, because as we'll see in the remaining best practices, deep learning introduces a lot of complexity. If you can avoid that complexity entirely, that's the best approach to dealing with the complexity. Now, if you have made the determination that deep learning is really the only way you're going to get this particular problem solved, then you have to take on that complexity. And the remaining best practices, 2 through 5, are all about how do we deal with the different kinds of complexity that arise when you choose to use deep learning in an enterprise application. Best practice number 2. Identify the 3 components of a deep learning model. As we noted in the first section of this talk, a deep learning model, when deployed in an application, has 3 parts. There's the graph, the underlying formula that this program is trying to calculate. There's the weights that parameterize the constants in that formula, and there's all the glue code that holds it together. It's important when you're looking at a given instance of a deep learning model to be able to clearly identify each of these 3 parts, to be able to pull them apart and manage them each in their appropriate way, because they have very different characteristics and they change at very different rates, and even that rate of change changes throughout the lifetime of the model. So in particular, when the model is being trained, the glue code is going to be a batch program that performs training. The graph is going to be actually code to construct the graph. And the weights, they're kind of an intermediate temporary data that the training program is saving just in case the power goes out and you have to restart this 5-day training process from the middle of the process. Well, when you complete training a model and you have a section of weights, the common practice is to take those weights, put them into a static data file in a well-known format. Same with the graph. Instead of shipping code to generate the graph, save the results of that code in a data file, which will be much smaller than the weights file, but still pretty substantial. And that glue code, when a model is deployed in an application, is going to turn into a microservice or a deployed function. Now that the format of these artifacts is changing as we move from training to inference, and during the lifetime of a model, the model is going to be retrained over and over again. So you're going back and forth between these 2 different formats. And we need to manage that change back and forth. And speaking of change, the rate of change of each of these parts of the model is going to be different depending on whether this is a new model that you've just deployed in your enterprise, or one that's reaching the latter part of its life cycle. At the beginning of the model life cycle, the glue code has been created, is kind of a stand-in for how the model will eventually integrate with the rest of your enterprise. The data science department is frequently tweaking the graph and frequently retraining the weights to get the results of the model better and better and better on the training data as you collect additional training data from your enterprise. After that's been going on for a while, the model kind of levels out into something that is good enough, where you have decided that you've found a good graph and you've got a good set of weights, and the only reason that you're producing new weights to parameterize this graph is to deal with drift in the application itself. Say the characteristics of whatever it is you're trying to predict change a bit over time. So you have infrequent changes to the weights, the graph just stays the same, but now your glue code is part of an application. And we know enterprise applications evolve. They can evolve quite quickly. And also, in addition to the evolution of the overall application itself, often when a model is reaching the end of its life cycle, it's very common for the developers to insert fixes for problems, known issues with the model, into the application logic itself, Say that there are certain types of text that your text model has difficulty with. Well, you can put static business logic into the glue code that will just kind of exclude that from what you pass to the model. So later in the model lifecycle, the glue code's changing more, the graph is pretty much frozen in place, and the weights are only changing on a maintenance basis. So each of these, and now we'll focus on the bottom 3 lines of this graph because training is more something that happens outside of the application layer. But to manage this, we need to follow a couple best practices underneath this master best practice. So first of all, it's important to store graphs and weights together because each set of weights only works with a particular graph. And some sets of weights will load with the wrong graph and produce subtly wrong answers. You want to avoid that at all costs. So always store the graphs data and the weights data together. All of the major deep learning frameworks provide facilities for storing these 2 data structures together. In TensorFlow, the facility is saved model. In PyTorch, it's Onyx. In Keras and Chainer, it's H5. Always use those facilities to store that weight and graph in the same file. And of course, once you've used these facilities, you'll have some very large binary files. A deep learning model file with the graph and the weights can easily be hundreds of megabytes, and you will be producing new sets of weights pretty frequently earlier on in the life cycle and still like weekly or monthly later on. So you need to have a good solution in place in your enterprise for managing these files over time. And you don't want to be throwing out these files. You want to retain a good amount of history. There are a number of different approaches. You can use existing facilities like object storage or your Git large file storage, but it's better if you have a lot of deep learning models to use some dedicated model management software such as Watson Machine Learning or Watson Machine Learning Accelerator. Third practice is manage your glue code as code, because glue code, although it's part of a deep learning model, it's still code. You should give it the same treatment that you give the rest of your application code. Make sure it is properly tracked in the source control. And when there's common code that's shared between that training phase and the inference phase, remember the training glue code is going to be a batch program, and your inference glue code is going to be a microservice. Anything that's common between the 2 of those should be factored out and stored in a separate library. Because if you have a subtle difference between the data transformations you're doing in training and during inference, you can get subtle errors in the results of the model. So just factor that out. Don't copy and paste there. Copy and paste is not something we want to do with code. Now, when you actually deploy the model, there are 2 high-level approaches for wrapping up these 3 components and deploying them in an application. The first is what I call the monolithic approach. That's where you take the graph, the weights, the glue code, and your favorite microservice framework, such as Flask, and stuff that all into a container. This is a very easy way to get started, an easy way to shoehorn a deep learning model into an existing container-based infrastructure like a Kubernetes cluster. The main issue with this in the long run is that that container is large and opaque, and you have to make a new version of the container anytime anything, regardless of how small, changes in the container. Particularly later in the life cycle of a model, when you're making a lot of changes to the glue code, you don't want to be respinning an opaque 500 megabyte container every time that you change one line of code. So it's better later on in the life cycle to move to what I call a decomposed approach to deploying the model. That's where you take the graph and the weights, which remember you're putting into one file, and you deploy them separately to a system that is dedicated to model management. And then the remaining code portion, that glue, you want to put into a system that is dedicated to running functions, such as a serverless function execution environment like OpenWhisk, or a microservice framework like Knative. The benefits of this is you get much better management and control of the execution of your models. You get better logging because a system dedicated to serving models is going to have much better logging of the inputs and outputs, which ties into our next past practice, which is collecting telemetry data about these models. And you're also going to have better management of the code if you keep the code in an environment that's meant for executing code. The con of this approach is that the learning curve is a bit higher. It takes a bit longer to get the end-to-end system set up. So you may want to use the monolithic approach initially to get up and running quickly with deep learning. Let's talk about the next best practice. We've hinted at logging and data acquisition in that last bit of best practice number 3. Well, best practice number 4 is all about data acquisition. Remember I said that there are 2 things that change when we moved from traditional machine learning to deep learning. One of them was the complexity of the formula, and the other was the size of the data. We need big data to deal with all the noise in our bad features. And this is a trend that goes across all the problems that you solve with deep learning. As the size of your data set goes up, you go through 3 different regimes. With the data, when the data is too small for the deep learning optimizer to be able to pick good weights, actually a traditional machine learning approach is going to do better. But as the data gets larger, the deep learning approach with the very large function and the very large data set starts exceeding the performance of something based on feature engineering. If you've committed to using deep learning, you want to move yourself to the right-hand side of this graph. And the way you do that is by gathering more data and continuing to gather more data on a continuous basis as your application is in production. How do you do this? Make sure that you capture every input that goes into your model in production. Make sure that you capture the corresponding business outcomes associated with each of these predictions. So if your model predicts that someone's a bad credit risk, you should capture information downstream about whether they turned out to be a bad credit risk in reality. And then once you've captured these different streams, you want to combine them together into a single consolidated format that you can hand off to your data scientists. It's important to have in place in your enterprise good tools for managing this data acquisition process. We include a number of good tools in our machine learning-based portfolios, systems like Watson Machine Learning or Watson Machine Learning Accelerator. We also have Watson OpenScale for managing the collection of this downstream business outcome information. And if you're looking at a completely open source solution, the Open Data Hub focuses again on this end-to-end collection of new training data. And finally, our 5th best practice is to plan for explainability. And this ties in actually to that collection of data, because explanations of deep learning models, it turns out, need a lot of data. Let me explain this. If you're going to deploy any model to your enterprise to use AI in part of a business process, you will come to a point where you need to explain the predictions that that model took. It could be that you have to explain to a regulator why you're making a choice. It could be that the answer is clearly wrong and you need to debug it. It could be that the answer is biased against certain groups and you need to say why and fix that. There are lots of reasons, but you will have to explain that result at some point. And because of the inherent complexity of the formulas inside these deep learning models, the only way that people have to explain them is empirically, by saying, on this data, the model produces this result. On that data, the model produces that result. If we look at what's different between these 2 data items, we can discern something about the characteristics of the model. So to be able to make these good empirical statements about a model, about what kinds of decisions it makes, you need, again, a lot of data. And then you need also some tools that are going to help you feed this data through accepted analyses to provide explanations of the model's behavior and to evaluate characteristics of those explanations, like is the model fair, is it exhibiting bias, that you'll need to provide as part of your explanation for what the model produced a result. And a number of tools that I can call out that help with this explanation process would be the open source toolkits AI Fairness 360 and AI Explainability 360, as well as our product IBM Watson OpenScale, which embeds the functionality of these toolkits and also provides some additional enterprise level functionality. So that's my 5 best practices for deploying deep learning in the enterprise. Use the right tool for the job, identify the 3 components, manage each component appropriately, build in data acquisition, and plan to use that data acquisition for explainability. A number of the product offerings in IBM's portfolio are focused on helping people deploying deep learning models to effectively use these different best practices. I've drawn a picture here on the screen of some of our offerings and how they map to these different best practices. In the quick demonstration I'm about to do, I'm going to focus on one of these, Watson machine learning. So I'm going to show how we can use Watson machine learning to identify the three components of the model, to manage each appropriately, and also get a little bit into how deploying to WML allows you to build data acquisition into your architecture. So let's move on to the tools and techniques part. And there we go. Okay, so in the interest of ease of exposition, I'm going to use a Jupyter notebook for this demonstration. Normally, because this is something of a DevOps operation, you would do this with scripts triggered by workflows. But with a Jupyter notebook, we can see the input and output of every step. So what I'm going to do here is I'm going to use Watson Machine Learning, our cloud service, to deploy a deep learning model. I'm going to walk you through the steps of that. And the model that I'm going to be using is a model from the Model Asset Exchange. This is a section of developer.ibm.com. To get to this, you can either search on your favorite search engine for Model Asset Exchange and optionally put IBM. It should show up as the first link. Or you can go to developer.ibm.com, look under More Open Source at IBM, and there it is, the Model Asset Exchange. The Model Asset Exchange is a section on developer.ibm.com where we keep a variety of state-of-the-art deep learning models. All of them are quickly deployable in seconds on your local laptop with a Docker container. Many of them can be retrained with custom training data to meet the characteristics of your particular application. And there are about 30 models on here, but the one I'm going to focus on today is a object detector model. And if we go to the landing page for this model, at the top of the landing page there's this link to get this model that takes you to the code for this deep learning model. And this repository has code both for training of the model and for inference. Because we're looking at deploying deep learning models to applications, we're going to focus on just the inference part. So our first best practice when using a deep learning model, when deploying a deep learning model, is remember, identify the three parts of the model. We need to find the graph, we need to find the weights, and we need to find the glue code. Well, if you look in the README for this file, with every model in the Model Asset Exchange, we include a detailed README with detailed technical information. And right there, we have a link to a file that, according to our best practices, again, groups the graph and the weights together. And we're storing that on cloud object storage so that it's easy to serve. If you were inside an enterprise, it would be better to use a model management system like Watson Machine Learning to serve this. But because this is on the Model Asset Exchange, we keep this data on cloud object storage. If you were to click on that, it would download the model file. I've already downloaded a copy of that to my environment in my Jupyter lab, though. It's right here. Inside of that is the file containing the graph and the weights all grouped together. It's in an older format, so the first thing I'm going to do is I'm just going to quickly convert it to a newer format. This is a TensorFlow model, by the way, using the popular framework TensorFlow. And I'll use my little cheat sheet here to grab the snippet of code that will convert that model from the older format to the newer format. In both cases, we're taking a model which would, a file which contains the graph and the weights, and converting it to a different file with the graph and the weights, just in a format that Watson Machine Learning can understand, the saved model format. Okay, now we have written out our model. You can see save model written to this location. Now what we're going to do is we'll just put the contents of that model. Save model format contains multiple files. Watson Machine Learning needs them in one file. We'll do cd saved model and tar cpzf saved model. There we go. Now we've created a tarball. You can see that tarball right here. And now if we're going to deploy this model to Watson Machine Learning, remember there are three parts. There's the graph and the weights, and there's also the glue code. Watson Machine Learning incorporates model management facilities. So we're going to use, in this case, because of Watson Machine Learning, we go back here, we're going to use the decomposed method for deploying the model, where we break it up into the graph and weights and the glue code separately. I should mention, by the way, that the Model Asset Exchange page for this model has a tutorial on how you would deploy this model using the monolithic method right up here, deploy Max models to IBM Cloud with Kubernetes. Here we're going to focus on Watson Machine Learning to get the more advanced capabilities of the system. And that means deploying it in a decomposed fashion. So first we need to get that weights and the graph out to Watson Machine Learning. And the way we do that is first package them up in the format that Watson Machine Learning uses. For TensorFlow models, that save model format. Then we need to define some metadata. And as it happens, I have created a little JSON file here with some metadata for this model, the field that Watson Machine Learning needs you to fill in. Let me just read that in quickly in my Python environment. Make the font bigger while we're at it. And we'll just print that out. There we go. We've loaded that JSON file. And now we've got just about everything we need. We got the model, rather the core of the model, and the metadata for that. So let's open a connection to Watson Machine Learning. There is a Python client for Watson Machine Learning, so in your CI scripts you can just connect. Here's how you do that. First you'll need some credentials. In this development environment, I'm keeping those in a local file. Then we can make a connection. Okay, now we're connected. Now we upload the model, or rather the core of the model. And so, repository, and the function for that is store model. What we're doing here is we're uploading the model to the model repository embedded into Watson Machine Learning. Watson Machine Learning has facilities for managing models and separate facilities for deploying them. One of the advantages of having a system that's dedicated to model management. And we also need to pass in the metadata, and we'll just print out the result. Okay, so Watson Machine Learning has deployed the model, has rather put the model into its model repository successfully. It's returned a bunch of metadata. If you were to do client.deployments.get details, it'll show you the details for all of the models that are in the repository. Currently, it's just the one that I have just deployed. But if you had 100 models in the repo, you would see 100 different sets of model information. Now we've got the model in the repository, we can create a deployment, create an endpoint for serving this model. So deployment details, and the call for that is client.deployments.create. And we're going to need the ID for the entity in the repository. That's stored in the model details that we just got. In the metadata field. And in a subfield called GUID. And we're going to need to give it a name. and we'll print out what that returns. And while it's doing that, I'll type something ahead. So we've successfully deployed the core of the model, the graph, and the weights. Now we just need to get at the URL that Watson Machine Learning generated. And there we have it. The core of this deep learning model is deployed. Now all we need to do is combine this with the glue code from the original model. Now the model came originally packaged up for monolithic deployment, and inside that monolithic deployment, inside this directory here, we got a core. There's a file with some Python glue code. Now I have helpfully taken that glue code, and I have, if I go over to my cheat sheet here, first off, we'll need an image. If we're going to run this model, it's an object detection model, so we'll need an image. So there's our image. And I've taken the glue code and translated into just some straight line Python code that I can run inside this notebook. Here's that straight line Python code. What this is doing is it's got some constants containing a table that maps category numbers to object names. And then we're going to take that input image, turn it into a series of numbers, because the formula in the core of the model requires numbers as features. Then we will pass those numbers to the graph that is deployed on Watson Machine Learning. And then we'll do some reformatting of the results so that they come back in a good format. And you can see what comes back from this is we have the detected objects in this picture: a boat, a person, a bicycle. Each one's got a bounding box. And you can see this is a picture that has boats, person, and bicycles, and half a car, but we don't get that because it's buried in a canal, and this model doesn't do so well on cars buried in canals. So to just tie this all back together, let's go back to the Model Asset Exchange. And on the landing page for this object detector model, we actually have an end-to-end web application that shows what you can do with this model if you deploy it inside the context of an application. So I will just take that image that I was using before, upload it to this application. There we have our image. It is running object detection with a deployed copy of this model, and there we get back a visual picture of the actual objects that were detected. The probability threshold of 50%. You lower it down, you get more detections until you get complete. If you lower the threshold too low, the model, of course, is detecting things that might be something with low probability. So it's a good idea to pick the right threshold. And there you have an end-to-end application that shows how you can use a deep learning model deployed from the Model Asset Exchange. So that is our end-to-end picture of how you use a technology like Watson Machine Learning to deploy a deep learning model. You see, first you identify the three parts, then package them appropriately, deploy them, ideally using a separate deployment for the core of the model and the glue code, so you can manage those parts appropriately, and put them into a system like Watson Machine Learning that's going to provide you with the logging and data capture capability to be able to get data about the inference requests, so that you can incorporate that data back into your end-to-end life cycle of being able to retrain the model and being able to do explainability of the model. So thank you very much for coming to my talk. Again, I am Fred Rice from the Center for Open Source Data and AI Technologies. We've talked today about deep learning models in the enterprise and applications. I've showed a few technologies in the demo. You can see the links to them on the screen right now: the Model Asset Exchange, that particular model, and the Watson Machine Learning system that I used. Thank you very much.